Okay, so chapter 4 is more about about how people viewed the universe some thousands of years ago and how our understanding of the universe evolved with time. We're gonna start with talking about the how ancient civilizations looked at the universe and how they pictured and imagined it. So this is the first model ever done for the universe. This is what we call the geocentric model. It's called the geocentric model because people back in the time, they thought that the Earth was at the center of the universe and that everything else in our night sky were assumed to be orbiting the Earth. So this is this is a sketch of a geocentric model. The Earth is at the center, the Sun orbits around the Earth, the Moon orbits around the Earth, and everything else, including the planets and the stars, were assumed to be orbiting around the Earth. This is what we call the geocentric model, or we call it sometimes an Earth-centered model. Now, this model was mainly proved by someone named Claudius Ptolemy. Ptolemy was a mathematician and astronomer, and he used to live in Egypt. He used to be responsible for the Great Library in Egypt. But anyway, Ptolemy believed in the geocentric model, and when you look at the night sky, you actually see that all of the stars are doing some kind of circles in the night sky, and this is what we have named as the diurnal motion of stars. And this is exactly what Ptolemy based his observation on. So when he was observing the sky, he saw that all of the stars were doing circles in our night sky, so the diurnal motion, and he also realized that the moon and the sun, they both rise from one side of Earth and then they set from the other side. So they also appear to be doing circles in our night skies. And this is why he believed in the geocentric model, and he proved the geocentric model, and he was actually defending his model. This is again a sketch for a geocentric model where the Earth was at the center of the universe, the Moon around the Earth, Mercury around the Earth, even the Sun were assumed to be orbiting around the Earth. So visually, this model makes sense, again, because all stars really appear to be doing circles in the night sky. And remember that at Ptolemy's time, and we're talking about thousands of years ago, in Ptolemy's time, the telescope hasn't been invented yet, so all of the observations were based on naked eye observation and not on telescopes. So this is also one of the reasons why people believed in the geocentric model. However, there was only one problem with Ptolemy, with the observations that were done by Ptolemy. You see, if you have a new law, or if you have a new theory, and this theory, according to Ptolemy, was that all stars orbit around the Earth and all planets orbit around the Earth, he based that theory on observation. But he had one problem only, and that is one of the planets in the night sky wasn't really doing a circle in the sky, but it was doing something we call backward motion. This is a sketch of a backward motion. So let me explain this. When you look at stars, and if you follow this mouse here, if you look at stars, they all appear to do circles in the night sky. And this is why everyone believed in the geocentric model. However, this star here, this object that you see in the night sky here, wasn't really doing a circle like all other stars, but it was doing some kind of a backward motion. So it was going up in the night sky. He assumed that this object would do a circle, but instead of doing a circle, it was going up, it did some kind of a backward motion, and then it went back to its original direction. So this is what we call retrograde motion. Now this was very complicated for Ptolemy and for everyone else, because all stars were doing circles in the night sky, but this object. So they couldn't explain it. They knew something was wrong with it, but they couldn't really explain it. So they kept on using the geocentric model, and they ignored the fact that one of the objects was not doing a circle but was doing a backward motion, or what we call a retrograde motion. Now, in the coming slides, I'm going to tell you why does this happen, why do we see this backward or retrograde motion, but I want you to know for now that Ptolemy couldn't explain it, and he kept on using the geocentric, or what we call the Earth-centered model of the universe. Let's talk a bit more about the retrograde motion. This is, so if I play this simulation, this is a star. I mean, I would expect that this star would do a circle in the night sky like all of other stars, but look at the behavior of this object. Instead of completing a circle, it went backwards, and then it's moving again into its original direction. So I'm going to repeat this. This is a star moving, then it slows down, and then it moves backwards, and then it continues with its original direction. So this is what confused everyone for thousands of years. They couldn't explain why this was happening. Yeah, so next came someone named Nicolaus Copernicus. Now, this guy tried to explain the retrograde motion. He didn't like, and he wasn't really convinced of the Earth-centered model. And after doing some research and some studies, Copernicus was able to come up with a new theory of the universe, and you can see it. You can see the sketch. You can see the sketch of his new theory right there. This is what we call the heliocentric model. It's a model that placed the sun at the center of the universe right there, and Copernicus assumed that Earth wasn't at the center of the universe, but the sun was at the center of the universe, and that all planets, including the Earth, were orbiting around the sun. This is what he called a heliocentric model. And remember that Copernicus came after around 1,400 years from Ptolemy. So for a very long time, people were still using the geocentric model until this guy came, and he was more convinced in the heliocentric model. Now, although the heliocentric model is not very correct, but at least it is better than the geocentric model, because it's not correct, because in the heliocentric model they assume that the sun is at the center of the universe and that all stars and planets orbit around the sun, and this is of course wrong. We know that all planets in our solar system orbit around the sun, but other stars in the Milky Way and in other places in the universe do not orbit around the sun. But at least his heliocentric model was, it made more sense than the geocentric model. And although he gave us this new, better theory of the universe, no one accepted it, and it was revoked and rejected. Now, during his work in the field of astronomy, he also tried to explain the retrograde motion, the backward motion. So in the coming two slides, I'm gonna show you why do we see the retrograde motion, why do we observe the backward motion. First, let me show you this one here. This is a simulation. This is the sun. These are the planets. This is how Copernicus viewed the solar system. Of course, it was better than the Ptolemaic model. So look, if I play this simulation, you realize that the first planet here, which is Mercury, is moving fast than the second planet, which is Mars. And Mars is moving faster than the third planet, which is Earth. And Earth is moving faster than the fourth planet. Sorry, this is not Mars, this is Venus. And Earth is moving faster than the fourth planet, which is Mars. The idea here is, the closer the planet is to its star, the faster it will be moving around its host star. And the further away the planet is from its star, the more time it will take for that planet to do one orbit. For example, look at this planet here. This planet, because it's really far away from the sun, it has to cover much more distances to do one complete cycle. And this is why this planet is moving slower than this planet, as an example. So this is directly related to the retrograde motion. So if I want to simplify this, this is the sun, this is the Earth, this is Mars. Earth is closer to the sun than Mars. So Earth will be moving faster than Mars. So if you are on Earth looking at Mars, look what happens. This is the view you're gonna see on Earth. So this is you on Earth looking at Mars. At some point, Earth will overtake the speed of, or the location of Mars, and Mars in this case will be located in, will be seen as if it's moving in a backward motion. It's a bit hard to explain this, that Copernicus was able to present the new heliocentric model of the universe, and he tried to explain the retrograde motion of the planet, or the backward motion. Now, sometimes after Copernicus came this guy. His name is Tycho. Tycho was a Danish astronomer and a philosopher, and he was very interested in knowing more about the universe and about space in general. And you see, at that time, everyone thought that the universe is static. Everyone believed that the universe is not changing and it will never change. They all thought that the universe has always been there and it will always stay there. So what happened in the 1500s at Tycho's time is that all of a sudden, and for an unknown reason, a new star appeared in the sky, and that star was very bright, and it began to grow dim until it faded away after 18 months. Now, it might not sound very important when you hear this phenomenon, but the thing is, remember, they thought that the universe does not change. Then all of a sudden, in 1572, a new star appeared in the sky, and then it faded away and it vanished. So just because this happened, this means that the universe is not static, and it also means that the universe can evolve and change. So Tycho tried to understand that new object that has appeared in the sky, and he tried to convince the community that the universe is not static and it can actually change and evolve with time. But again, people didn't like his ideas because it contradicted with the general belief of a static universe. But Tycho took things further, really. He didn't only say that the universe is changing because he saw a new object in the sky. What he tried to do was he tried to find the distance to that star. And one of the ways to find distances to stars were using what we call parallax. Now, I'm not sure if he was very accurate in finding the distance to that new object that has appeared in the sky, but he did try to apply the parallax method. So, a parallax method, just that you know, is a method that astronomers use to find distances to stars using some trigonometric relationships. The parallax method is a method that relies on looking at the same object from two different points of views. Meaning what? So, let's say you are on Earth. Earth spins around its axis once every 24 hours. So if you are located here now, after 12 hours, you're going to be located at the other end of Earth. This is how things go because Earth is spinning. So if you look at this star, and then you draw an imaginary line, and then you wait 12 more hours and then you are located here, and then you look again at the same star, you would have created a triangle. And by creating this triangle, you can use some trigonometric functions to find the distance to that nearby object. This is exactly what Tycho has tried to do. He looked at the star from two different points of view, and he tried to find the distance to that star. And what he has found is that that star, or that thing that has appeared in the night sky, must have been really, really far away, further than we have ever thought. So it was located at the outer boundaries of the universe. So this is when people started realizing that the universe must be much larger than we have ever thought. And by the way, what he has seen, well, he didn't know it at that time, but what he has seen was nothing but an explosion of a star, or what you call a supernova explosion. This is the simulation of a supernova explosion. This is what he has seen, and this is why the new star appeared in the sky for around 18 months. So Tycho, if you wanna, summarize what Tycho has done, he did two main things. First of all, he was one of the first guys to start talking about a non-static universe, in other words, a changing universe, an evolving universe. And second of all, he tried to find the distance to that new star that appeared in the night sky that we know today was nothing but a supernova. He tried to find the distance to that supernova, and he realized that that object is really far away, and thus we started to believe that the universe is much larger than we have ever thought. So this was Tycho's work. So after Tycho came someone named Johannes Kepler. Kepler, just that I stress this out, at this point people still believed in the geocentric model, although Copernicus talked about the heliocentric model, but his model wasn't really accepted. So this guy came, Johannes Kepler. People at that time thought of a geocentric model, and also they thought that all planets orbit in the night sky or move in the night skies in circles. So Kepler came, he was more interested in the motion of the planets, the motion of the stars, and the motion of the celestial bodies, and he really came up with three very important laws. Now I'm gonna go over these laws. The first one is, it says the following: the orbit of a planet around the sun is an ellipse with the sun at one focus. And let me explain. Look, this is a star, and this is in blue. This is how a planet would orbit around its host star. It is obvious that this orbit is not circular, it's an elongated circle, or what we call an ellipse, and you can see that with the simulation. So at this point the planet is further away from its star, and if we wait some more months you will realize that the planet will be a bit closer to its star. And this is simply what Kepler has told us. He said again that a planet like Earth would orbit around its star, not in a circle but in an ellipse, and that the sun is usually not located at the center but at one of the focal points. So it's either more to the right or more to the left of the central point. So as the Earth orbits around its star, the sun, the planet is sometimes closer to the star, and sometimes when it is here it is further away from its star. And this doesn't apply for Earth and the sun system, it applies for everything there is in the universe. This is how gravity works really. So for example, a star would orbit around a black hole in an ellipse with the black hole at one of the focal points. The moon orbits around the Earth in an ellipse where the Earth is at one of the focal points, and so on. So he tried to tell us that stuff move in ellipses like these ones in the universe and not in circles. This was his first law. Now, Kepler's second law, maybe you will not find this, maybe you're not going to be able to relate so much to Kepler's second law, but Kepler's second law is called the laws of equal areas. And let me elaborate. You see, if I go back to this sketch here, this is the planet orbiting around its star. When the planet is closer to its star, so in this area, it's going to be moving fast. But when the planet is further away from its star, like when it's reaching this point, it's going to be moving at a slower rate because it is further away from the sun, which gives it gravity. Excuse me. So Kepler said that the area of this triangle here will be always equal to the area of that triangle if the time taken for the planet to move from this point to that point is equal to the time taken for the planet to move from this point to that point. In other words, let's look at this sketch here. So assume it took the Earth 1 month to move from this point to that point, and it took 1 month the Earth to move from this point to this point. Kepler said the following: if you connect the lines here and you form a triangle, and if you connect the lines and form another triangle, the area here will be always equal to the area there. This is what he has said. This is called Kepler's second law, the laws of equal areas. Again, you might not find this you might not find many applications where you in specific can use this law, but it's a very important law that we use in trying to study the motion of all the objects in the night sky. So let's move to Kepler's third law. Kepler's third law is kind of an equation. It says the following: p square is proportional, not equal, proportional to a cube. P is the period, so it's the period of the planet to orbit around its star. As an example, the period of Earth is 1 year, 365 days. It takes Earth 1 year to orbit around the Sun. The period of Mercury is 88 days. It takes Mercury 88 days to orbit around the Sun. So what he did was he came up with a law right there, and it's right here also to be more specific. He came with a law that would relate the period of a planet to its distance. So if you look at the simulation, assume this is Mercury, the blue one. Mercury is close to the Sun, so it is moving faster, so the period is short, 88 days. While if you look at the green planet right there, look, the period of the green planet is larger than the period of the blue planet, because the green planet has to move more, it has to cover more distances to do one complete orbit. And as you can see, the A, which is the distance between the Sun and Mercury, is smaller than the distance between the Sun and the green planet. So what Kepler has said is, as you increase the distance between the star and its planet, the period will increase. This is what he has said. So if you want to think of an example, you have Earth, and then you have the Mars. Mars is the fourth planet, Earth is the third planet. So Earth has a smaller distance to the Sun, it has a smaller A. And Mars has a larger distance to the Sun. So you can just directly say that the period of Mars will be larger than the period of Earth, because Mars is further away from the Sun than Earth. So this is what this relationship is telling us. As you increase A, as you increase the distance between the star and its planet, the period will increase. The planet will take longer time to do one complete orbit around its star. And this applies again to everything, not only for stars and planets, but to black holes and galaxies and neutron stars and everything else we have in the universe. So yeah, until this point, no one has ever used a telescope. Everybody was using, their naked eye observations. No tools were used until this guy came, Galileo, if you have heard of this name before. Well, to brief this out, Galileo, he was very interested in space, of course. He's a great astronomer, a great philosopher. He's considered to be the father of modern science and modern astronomy, because he was the first person to use a telescope to observe the universe. And what Galileo has done, he used this telescope to observe the stars, and he made so many discoveries. I mean, in the end, he was the first to use a telescope, so of course he would have found so many discoveries. From these discoveries were the mountains of the moon, the phases of Venus, sunspots, and so on. But perhaps the most important discovery that I want to discuss is this one. He discovered 4 moons. This is Jupiter. He discovered 1, 2, 3, 4 moons that were orbiting Jupiter and not Earth. Of course, we know today that Jupiter has so many moons, so many more moons, but at that time it was a great discovery, because for the first time ever we have discovered objects that were orbiting Jupiter and not Earth. And so this works well with the heliocentric model that Copernicus suggested. So for the first time ever, we can finally confirm the heliocentric model, and that was done at Galileo's time. So I hope it's clear, and let me just say this again. What Galileo has done, he found planets, he found satellites, moons, that were orbiting something other than Earth. According to the geocentric model, everything in the universe orbits around the Earth. But his observation detected something that were, it detected objects that were orbiting Jupiter and not Earth, and thus the geocentric model was wrong, and the heliocentric model was accepted by them. So after Galileo came Newton. We're not gonna talk a lot about Newton, but what you need to know is that Newton was the guy to discover gravity. He was the person to give us 3 laws to describe gravity, and this is something we will discuss later. We're gonna be talking more about gravity. So yeah, this is all about chapter 4. If I wanna summarize what we have talked about, we talked first about the geocentric model, how does it behave, what people thought about it, how Ptolemy came up with this model, and we also talked about one of the problems for the geocentric model, which was the retrograde motion, the backward motion of stars. And we also explained a bit about the retrograde motion and why it happens. We then talked about Copernicus in the 1500s. He tried to convince people with the heliocentric model. No one was convinced, so his theory was revoked and rejected. And then we talked about Tycho and how he thought that the universe is larger than we have ever thought, and how he discovered that the universe is changing and not static. We also talked about Galileo, how he used the telescope. About Kepler, how he gave us the new laws of motions, so the 3 laws of motion. And then we talked about Galileo and his discovery, and then we talked about Newton, and that would be it. This is a very brief explanation about the history of our understanding of the universe.